Now, before we solve the third problem, and let's get something out of the way here, you're given the slope of a ramp. Now, you can easily enough calculate the arctangent of the slope, or the arctangent of the negative of the slope, in order to get the angle of the slope. And then you can take the sine and cosine of the angle, break the initial velocity vector into its x and y components, and proceed with the problem. And there's nothing really wrong with that. But there are quicker and more efficient ways to do this. Now, I'm going to show you one, and then I'm going to show you another one that's equivalent to it that's even easier. So what we have is the angle of the ramp is the arctangent of the negative rise over run. The way I've got this drawn, where this is the angle of the ramp from the positive x-axis around to here. This, if that's the angle of the ramp, then that's the arctangent of negative rise over run. Because if you do from here to here, you're going to have a negative rise and a positive run. If you go from here to here, you're going to have a negative run and a positive rise. Either way, the slope, when you come out into the second quadrant here, is going to be, or the angle is going to be the arctangent of the negative of the slope. And that'll also be true in the fourth quadrant, because the arctangent doesn't distinguish between the first and third quadrant, and it doesn't distinguish between the second and fourth quadrant for reasons that you should understand if you've got a solid trigonometry background. If you don't, you should think that one through. Okay, so the angle of our initial velocity here for a ball rolling down this ramp and off the ramp, which is what we're dealing with in this problem, is pi radians from the angle of the ramp as I've got it drawn here. It's going to be down in the fourth quadrant. Now, there are many ways this could be pictured, and you could picture it even more directly. The slope of this vector is also going to be negative, and the angle here, or the angle around here, would again be an arctangent of the negative of the slope. Well, that being as it is, let's draw a picture here where we've got 1 here, and we've got the negative of the slope here, and we've got a triangle that has an x component, or a side parallel to the x-axis equal to 1, and a rise, or a side parallel to the y-axis equal to the negative of the slope. The hypotenuse is 1 plus the square of the slope. Now, the angle here at this vertex of the triangle has a tangent that's equal to the negative of the slope, so that this angle is an arctangent of the negative of the slope. So that if we want to find the sine or the cosine of this angle, which we would want to do in order to find the components of this initial velocity, we would have to find the cosine of the arctangent of the negative of the slope. How do we find the cosine of the arctangent of the negative of the slope? Well, right here, again, this angle is the arctangent. Here we've got this side and this side of the triangle. We can calculate the hypotenuse, 1 plus slope squared. And the cosine is just this side over this side, 1 over the square root of 1 plus the square of the slope. So the cosine of the theta VEL, which is the theta for the initial velocity vector, is 1 over the square root of 1 plus the square of the slope. Now, that's easily approximated with good accuracy. Slope is 0.15. 0.15 squared is 0.0225, and the square root of 1 plus a number close to 1 is twice as close to 1. This differs from 1 by 0.0225, so that this is going to differ from 1 by half of that, which would be 0.0125, which I round off to 0.013. And then the reciprocal of 1 plus 0.013 is about 1 minus 0.013. The reciprocal of a number close to 1 is, let's say, the reciprocal of a number a little greater than 1 is a number a little less than 1, and the number is a little less than 1 by the same amount that this number is a little greater than 1. We'll talk about that in a second. In any case, we get a good approximation of 0.99, and 0.987 would even be a better approximation. Then the sine of that angle, which would be the sine of the arctangent of negative of the slope, Here's the arctangent and negative of the slope. Sine is this over this. Negative slope over the square root of 1 plus slope squared. Using the same approximation down here, and the negative of the slope here. This number is so close to 1 that it's not going to affect the 0.15. It's still going to be 0.15, still going to round to 0.15. So the sine of that angle is going to be negative 0.15. So when we calculate the components of the initial velocity, assuming the picture is like this, and you could have drawn the picture where the ramp is coming down this way and everything would be in the fourth quadrant, but same procedures would apply. You're going to have pretty good values for the sine and the cosine of that angle. And matter of fact, if you do this with a lot of accuracy, you get a very, very good approximation. Now, why is it that the square root of 1 plus a number close to 1 is 1 plus half that number? Okay, or very close to 1 plus half that number. Well, small epsilon approximation. If epsilon is a small number, then the square root of 1 plus epsilon is approximately 1 plus epsilon over 2. That says the same thing I said here, where the square root is twice as close to 1 as the number itself. Now, we're getting a thunderstorm. I'm just going to stop to lock in this part of the video. Lights have already flickered, and if the computer goes down, then the video gets lost. Okay. Okay. Why should the square root of 1 plus epsilon be close to 1 plus epsilon over 2? Well, it's because if you square 1 plus epsilon over 2, you get something very close to 1 plus epsilon. Okay? 1 plus epsilon over 2 quantity squared, and you can work that out. I mean, it's very simple. Distributive law, or use a special product, is 1 plus epsilon squared over 4. If epsilon is a small number, then epsilon squared is epsilon times as small. So it's much tinier than epsilon. So epsilon squared is going to be a very tiny number, and for purposes of approximation, could well be negligible. And in this case, it pretty much is. If you do this calculation and compare it with 0.987, you're going to come out very, very close. Okay. And why should 1 over 1 plus epsilon be close to 1 minus epsilon? Well, because I multiply both sides by 1 plus epsilon, you get 1 minus epsilon times 1 plus epsilon equals 1. Now, that's not exactly true, but 1 plus epsilon times 1 minus epsilon is 1 minus epsilon squared. Epsilon squared is, again, if epsilon is small, epsilon squared is really tiny. So this is really close to 1. So this is a good approximation. And again, for the numbers that we have here, our approximation is quite good. Now, just another comment. The stuff I showed you about the arctangent and negative slope, the cosine of the arctangent of a number calculated by drawing this triangle, you really need to know that. That becomes important in a lot of applications. You didn't really need it here. You know the slope, so you can just set up a triangle with 1 slope, square root of 1 plus slope squared, and immediately calculate the sine and cosine of this angle here. You don't need the arctangent of negative slope notation in order to do that. That's just a common sense calculation. So you can even bypass this, but I wanted to address this as well as this, so that you could get this directly from this triangle or from this triangle. Whatever the rise is, whatever the run is, this is the square root of rise squared plus run squared. Many ways to get the ratios of the sides that are involved with the sine and the cosine.